Okay, let us start now. So in the last class, if you remember, we were discussing about causality. So what is causality? Causality is basically the process of identification of cause-effect relationship among different pairs of or between a set of variables. So that is, when can we say that one variable is the cause and another variable is the effect? That can happen if all other variables remaining unchanged. If we if the variable if the variable x changes, then the variable y changes in a particular way. But if the variable y changes in any particular way, then variable x does not, it cannot be said that variable x will change. If this happens, then we can say that all other conditions remaining unchanged, there exists a cause-effect relationship between x and y. That is, x is the cause and y is the effect. So like we had actually discussed an algorithmic framework in which this kind of a thing can be or this kind of a relationship can be identified. So like we had talked about the basic, that is, we had drawn some parallels between this causality or cause identification problem and the feature selection problem of machine learning.
Machine learning.
That is to say, like whenever we have a particular like a variable which we are considering as the effect and we are looking for its causes, then that problem can somehow be mapped to the problem of prediction in machine learning, where we have like a large number of potential predictors of a particular variable y, and we are basically among those predictors we are trying to identify which are the important predictors. So that is called the feature selection problem. And so for that, we had just briefly discussed, without getting into the details of anything, the two algorithms called lasso, which or lasso based linear regression, which allows us to identify the important features. And apart from that, we had also mentioned another algorithm called decision trees or random forest. We are, without going into that, without actually seeing what that algorithm does. But we had also mentioned that these algorithms struggle in the presence of confounders. So what is confounder? Does anyone remember what is confounder? Quick. Anyone remembers what is a confounder? So if you remember, last class we were studying this kind of some spurious relationships, right? Some spurious relationships like this one, that we have a we are measuring two things. One is the the spending behind science and technology, and the other is the suicides per year. And we found that those two things to be strongly correlated to each other. But but clearly that was not the case, that it cannot be that one of them is the cause and another is the effect. So we concluded that this is happening because of confounders. So what is confounder?
Sir, any other variable from those features that are selected that can affect the results?
So basically, it is such a variable which affects both the cause and the effect. I mean, or rather, it affects. That is, suppose we are considering whether we are calling this as x and this is y, and we are trying to understand whether one is a cause and the other is the effect. Then in such a situation, a confounder is such the third variable which influences both x and y. So in this case also, when we are uh, in this case, when we are when there is a possible effect for which we are looking for causes, and we have a very large number of potential causes, then we are trying to identify which of them are maybe actually causes. With the help of something like a lasso linear regression, such a problem, this approach may suffer if there are confounders. That is to say, the large number of potential predictors or potential causal factors which we have decided, if they themselves have some cause effect relationships among themselves, then they are known as the confounders. And in the presence of such effects, then these algorithms do not do well. So for that, we had discussed something called double machine learning, or DML, which basically is like a two-step lasso regression. So now, so today, what we will do is, in the last class, we had not gone into details of any of those algorithms, like how linear regression works, or how lasso regression works, or decision tree works, etc. So that's what we are going to do today. Let us consider what this economic problem as the basis of this. So, like recommender systems is something which all of you are familiar with. So all these big giants like say Amazon and say Booking.com and so on, like all of them are basically recommendation systems which allow you to search for certain items, purchase them, and also it also allows you to give feedback, and it is on the basis of the user feedbacks that they recommend these items to other users. Say for example, this is an example from Booking.com. So you can see that different people have, some 195 people have given ratings to this particular guest house, and you can see out of 10 the average rating is 7.2. In this case it's 6.3. Like in case of this laptop, so there are like this is from Amazon, so there are like 5 people have given ratings, so 44 people have given ratings out of 5, and the average rating seems to be 4. So so these, there is a very important, like there is a lot of economics behind these ratings, because it's like because which product is going to be promoted or recommended by these search engines, that depends a lot on these ratings. Typically the search engines will try to predict, that is, I will give I as a consumer will give high ratings to which products, and that is how, and it is such products that it will show to me. Why? Now, because like if I am giving if I am likely to give high ratings to a particular thing, to a particular item, that means I will like that item. So if they recommend that to me, basically they are recommending to things that are according to my needs or according to my tastes, right? So basically it is important for these like it is important for the business purpose of these search engines to understand and to model uh, the behaviors of these users as far as the reviews are concerned. Okay, so like now that is, different people of course give reviews in different ways. There are some people who give like mostly binarized kind of ratings, that is they either give very low ratings or they give very high ratings. Some other people, their reviews are much more nuanced, that is they actually differentiate between somewhat satisfied and somewhat dissatisfied and all these kinds of things. The same can be said about various types of articles or items or services also. So there may be some items or some services about which most people like have very polarized opinions, that is either they are very satisfied or they are very dissatisfied. Like for example, in that case we may see a this kind of a distribution. On the other hand, there may be some items with which many people may have a nuanced opinion, in which case we may see a like a distribution of these of ratings in the ways. Now the question might arise that how do users rate a particular product? So it can be now a particular product. Say for example, suppose I am buying a camera, then a camera can have various features. Say for example, its picture quality. If it is a video camera, then its video rate, its value for money, or even some aesthetic factors like its color, or maybe simply which company it is has built that camera. These are all potential factors which influence the ratings of a person. Now, these ratings may not always be rational. I mean, if we are buying a camera, then whether it's a white camera or a black camera, why should it actually matter? It's the camera's performance which should matter. But actually, that's not the case, because it has been found in various market surveys that people tend to have their like favorite aesthetics as far as items are concerned, and that sense of aesthetics can impact their rating behavior also. Similarly, so basically the thing is that when I am rating a particular product, it's really the product has several facets or several attributes, and what I am mentally or subconsciously doing is that I am giving ratings to each of those facets, and the overall rating which I give is some kind of a function which may be a linear function or a non-linear function or something of the ratings which I have given to the individual facets. So here you can see the like this is something which many of you may have seen at some point. This is a feedback formed by the Indian Railways, where some 18 things are given to you, some 18 different services are given to you, and you have to give a feedback to each of them, and finally on the basis of that they will actually calculate a score, that is either you can calculate or they also can calculate an overall score. Now there can be, as far as this process of ranking various facets is concerned, people may display different types of behaviors. Say for example, here like there is a product in which there are 5 different facets, and in user 1 has given the following ratings to each of the different facets out of 5. That means they are mostly satisfied, borderline satisfied with all 4 facets, and reasonably satisfied on the 5th facet. Here on the other hand, they are very satisfied with one particular facet, reasonably satisfied with many other facets, but clearly dissatisfied with one particular facet. Now, in these two cases, what is the overall rating which that user will give? So like you can see that there is a difference. In this case, they are reasonably satisfied in most matters. In this case, they are very satisfied in one matter, very dissatisfied in another matter, and reasonably satisfied in the other matters. So we cannot really say at this point what their final rating is going to be. Why? Because, for example, this person is very satisfied about the second feature, but very dissatisfied about the third feature. Now, if it happens that these are equally important to the user, then of course they will probably give an average rating like 3 or 4. But it may happen that this third feature is really the feature which this person was most interested in, while the second feature is not particularly useful or is particularly important for this particular user. So in that case, it's possible that because the third feature is what the person was really looking for and he is dissatisfied with that, so it's possible that he or she may actually give low ratings overall to the entire thing. So now we may of course now how exactly a particular person combines the ratings to the individual features may be like a very difficult thing to understand, and it may vary from one user to another user also. But when we are building a model, we'll have to make some kind of an assumption. So the simplest model in this case is, of course, the linear model. That is to say, we assume that the ith user has that is the different weightages, or which are basically some measure of their importance they attach to each of the features. And so the weightage so when they are giving an overall rating to that feature, I mean to that item, they are basically giving weightage, they are giving ratings to each of the individual features, which I denote by xij, I meaning the user and j meaning the particular feature, and I am measuring and I am weighing each of those individual ratings by wij, which basically indicates the importance of that particular feature, the jth feature, to the ith user. Plus there is a bias term called bi, because there are some users who are naturally inclined to giving high ratings, and there may be some users who are naturally inclined to giving low ratings. So an user specific bias bi is also included here. So as you can see, this is a linear function. Okay, now so then the question is, if I am a company like Amazon, and if I want to recommend some items to a particular user, what I will try to do is that basically based on based on that particular user's previous ratings, I will try to understand these wij, that is for every user how much importance they attach to that particular weightage. And now that is the yi's may be known to me, the xij's will also be known to me. So what is yi? Yi is the rating which the user has given, the ith user has given to the overall item, and xij is the basically the ratings which the ith user has given to the jth feature of the rating. So like given these two things, I will have to estimate wij and bi. wij meaning the importance of the jth feature to the ith user, and bi is of course the bias of the user. So these are the things which I will have to estimate. How? So that is where machine learning comes in. So what is the total number of things to be estimated like this? So there are m users and n features. So total mn number of features. And each of the users has a bias also. So total mn plus m terms, unknown terms are there, which all have to be estimated from the data. Okay. So that is the total number of parameters to be estimated, but then we can say that that is too many parameters. That is we have m users, and from m users we are having to, based on that we are being forced to estimate mn plus m number of parameters, which is quite large. Okay, so that's so too many features, or too many parameters makes a model difficult to estimate. So we usually try to reduce the number of parameters as much as possible. In other words, we go for simpler model. A simple model is something which has less parameters. A complex model is something which has more parameters. Okay, so so here we make an approximation. What is the approximation? So this is the approximation. So now can any of you tell me what is the difference between this model and this relaxed model, and what is its interpretation? Yes, anyone wants to venture? What's the difference between this model and this model? Ashwin Tripathi, can you tell me what's the difference between this model and this model?
Hello.
Yes. Yes, Ashwin, tell me.
Sorry, sir. I don't know. Sorry.
You don't know. Who knows? Adhiraj Rastogi, want to guess what's the difference between this model and this model?
Sir, for each for the first model, there are different biases, and for the second model, the bias is the same. And for the first model, there are different weights for all those features, and for the second model, the weights are just like with respect to the items only.
So, that's right. So basically, the big difference from here to here, that as you can see, what is self-evident is that this index I, this is present in the first model. This has disappeared in the second model. Now, I stands for what? I stands for user. I stands for user, and J stands for feature. So here, like Wij is the importance which the ith user attaches to the jth feature. So now here I am, instead of Wij, I am saying Wj. That means what? That means simply the importance of the jth feature. So so that means what? That means I am assuming that the importance here I was considering that the importance of the jth feature was particular to the ith user, but here the importance of the jth feature here we are assuming is uniform. It's like it's common across all the users. Okay. So now we come to so the question is how to estimate all those all those parameter values. So the answer to it is linear regression. So like the general recipe here is something which we had already outlined in the last class. We have to define a model with parameters WB. We have to define a measure on how well the model can fit the final scores, and then choose the model choose those model parameters which improves that measure. So so basically we have to define something known as a loss function and choose the parameters w, b, etc. in such a way that that loss function is minimized. So the loss function is basically a measure of fit, that is how well the whichever model I am coming up with, how well it fits the data. Means what? How well that model is able to predict the data. So here this is my proposed model, that is like my claim is that the if that is if xij is the set of ratings to the individual features and wj these are the weights of the individual features, then the final rating of the item by the ith user is going to be hi. Okay, but this is what my prediction is. But of course, I know that the correct rating by the ith user to this item is yi. So what I am doing is I am going to measure how different yi is from hi, and accordingly I will build this loss function. Okay. So now comes the actual thing of linear regression. I have defined the loss for user I. Similarly, over all the users, I will add up this loss so that I get a total amount of loss. Remember, I know the yi's, I know the xij's, but I don't know w and b in this thing. So then what I am going to do, I am trying to calculate the w and b in such a way that the overall loss is minimized. Right now, minimizing this loss means what? Minimizing this loss means hi should be as close to yi as possible. Only then will the loss be minimized. Okay, so when this total loss is minimized over all the m users, to achieve that, what do I have to do to select the w and b? Obviously, since this is a function of w and b, I will have to take the derivative of this function with respect to the w's and b's. So there are how many w's? For each of the features there is a w. So if there are n features, there are w variables like this in the equation. So sorry, I mean in the function. So I will have to differentiate partially this thing with respect to each of those w's and equate them to 0, so that I get a total n equations. Apart from that, b is also there, so I have to differentiate with respect to b also. So total n plus 1 equations I get, and the number of variables I have is also n plus 1. For every feature there is a w and there is a b, so total n plus 1 features. When I differentiate, I will get n plus 1 equations. I will equate them to 0. I will solve those equations simultaneously, and I will get an expression for w like this. So this is the expression for w. So like as you can see, you can actually work out this mathematics also if you want to. So basically what is happening? So first of all, I am calculating x bar and y bar. What is x bar? X bar is basically the for each of the that is for okay, so like this is just assuming that there is only one feature. Let us say j, that is n equal to 1. Okay, so in that case, what has happened is that to the individual features, what all ratings I have given, like you are summing up like this and you are taking the average, so that you get x bar. Sorry, this is not n, this will be m. There are m number of users who have given the rating, so this is m, and here also this is m. So accordingly, so you are getting x bar and y bar, the mean values of the different of the feature rating as well as the individual rating. And after that, you subtract the mean rating from each of the actual ratings, so that you get you can actually estimate this expression for w which has been given here. Okay, so these mathematics you can work out. So this is the standard linear regression for which there are packages on Python also. So you can there are these either you can directly go for the optimization, or you can use import the various libraries that are available in Python for this purpose. So so this is an exercise which you can try. Now so what happens once you have got it? So suppose you have got the w's and the b's, then how does it help you? So that basically when you get a new model, a new item, you can actually use those W. So now we have got the weightage of the different features. So now when you have the new item and the different users are giving scores to each of the items, so now you can know how or what their actual what the predicted average ratings of that thing is of that new item is going to look like. Okay, so like now suppose that there is a now a new item has come, so let us call it as a new camera. So we know that, and we also suppose we like based on the analysis which we told earlier. So we have tried to understand the relative weightage of the different features. So in a let us say that the various features of the camera are as follows: the resolution, that is the picture quality, the battery life, its memory, flash, weight, size, etc. Some of them are functional attributes, or some functional features. The others are mostly based on aesthetics. Okay, so apart from that, now the weights of the features, let us say, have also been calculated, and let us say that if you consider one particular feature, let us say the resolution, suppose it has come out to be 0.54, right? That is, when we solve this linear regression problem, each of those features got certain weightage. So for this particular feature called the resolution, let's say that the weightage is 0.54. Okay, now for the new camera, let us say for this particular camera, let's say the resolution has come to be 5 megapixel, and I know that its weight is 5.4. So here, by looking at the ratings which different people have given to this feature, so like you can actually also calculate what is the average rating which people have given to resolution, and in this case it comes to 4.0. Okay, so the similar analysis can be done for the other features also. So so what can you now do? Let us say that okay, let us say that there is a third feature, memory. For that also we have been able to calculate its weightage, and you have also been able to like you also have the average ratings of the memory feature 4.5. Okay, so now what you have to do is you have to predict the overall average rating. Okay, so now you know, for each of the three different features that we considered of this of this particular camera model, we know that there are these three the important features. So the first one is the resolution, whose weight is 0.54. The second is the battery life, whose weight is 0.36. The third is the this memory, whose rating is 0.1. And in each of the cases, the average ratings by the different users are as follows: 4.0, 3.8, and 4.5. Okay. So then, so what is the overall average rating of this camera going to be? So you can just do this weighted average according to the linear regression formula. You know what are the weights of the different features. You know what are the average ratings of the different features. So you know what is going to be the overall average rating for the camera. So this will be like 4 stars out of 5, you can say. Okay. So now what does this mean? These numbers mean 0.54, 0.36, 0.1. These, as I said, are the weights of the three different features which I considered here. So a higher weight means, a higher positive weight means, if that feature is good, then then people will like the overall product also more. Now if it has a lesser weight, a lesser positive weight means, if that feature, even if that feature is good, it will, like, people may like that particular feature, but it may not make so much of a difference on the overall ratings of the product. So, okay, similarly there can be some negative features also, though that is unlikely. Now suppose I am interested to understand specifically which are the important features. That is to say, instead, suppose there are lots of features are possible, just like we considered 3 features in case of the camera. So similarly, lots of features are possible, out of which maybe only a few of them actually matter to the user. That is, it is unlikely that I will that is, when I am rating a camera, it is unlikely that what its color is or what its weight is going to play such an important role behind the ratings. I mean, for some users, as I said earlier, also these things may be useful or important attributes. But here we are considering WJ, means that like it is no longer these weights are no longer specific to a particular user, but like common to all users. So that means even if there are some users, one or two users who are obsessed with the color of the camera, they will be like very less. So their weightage will not matter so much. So this is like saying that so basically what we are interested here is we are interested in trying to filter out all the non-useful features and focus only on the useful features. So how can we do that? That is by such a thing can happen if like almost all the elements or all the features have like very low or even zero weightage, and only those features which are important for the overall ratings, only those have high or significant weightage. In other words, I want most of that is, if I want to identify only the few features which are really important in making the predictions, I would want most of the elements in this W to go to 0. The other, only the really important ones, they will take non-zero values. And it is like here that we make the analogy with the causal relation or cause identification. So remember, in the last class we are saying that we will go for some 1000 possible potential predictors or potential causes, and out of which we will try to make sure that like it's a like only a small number of them are selected. That is the same as this feature selection problem. That is, we want to identify the important features and filter out the non-important features, and that can be achieved by with the help of this W vector. How? That is by forcing this W vector to be sparse. Now we want such a W vector such that most of its elements are 0. Okay, that means what? That means it's a sparse vector. So how? So basically, so like when we are solving this linear regression problem earlier, that is when I came up with this formula for calculating the W. Here it's not guaranteed anywhere this W vector which I will get is sparse, or many of its elements are going to be 0. I mean, if it comes out 0, fine. If it doesn't come out to be 0, then also fine. My task so far was to fit the data to the observations. That is, my predicted value should be as close as possible to the observed value. That was the only thing I was concerned with till now. But now I have an additional requirement also. I want W to be sparse. Okay. Now the general recipe to achieve this kind of a thing is using a regularization function called FW. Now FW is such a function, the regularizer is such a function which should have a low value if the W is suitable and a high value if W is not suitable. Now in this case, what do I mean by suitability? I mean sparsity. So that basically it means that if I want to define a function f which will have a low value when W is sparse, and it will have a high value W when the thing is when the W is not sparse. Okay. So now this is what so before we come to what that function can be, so this is what my this function, overall objective function of the optimization problem, now looks like. So LWB is basically the earlier loss function, the squared error which we talked about earlier. That's basically measuring how well my predicted Y matches the actual Y, the squared difference between them. This is that same thing as earlier. Now to that I am assuming I'm adding plus lambda FW. Now what is FW? FW is the regularization function which I mentioned to you earlier. And what is this lambda? So lambda basically is the weightage or the relative weightage between these two things. So there are two contrasting objectives which I have. One is to make the data or make the model fit the data. The other is to force the W vector to have the properties which I want, in with this case that is sparsity. Now it may happen that the W for which this part is minimized is not at all a sparse W. Maybe it has high values of all the elements. So in that case, I will be scoring badly on this particular function. And it may also happen that if I go for any sparse W, then I may be doing badly on this part, means I will not be able to fit the model onto the data. So a balance has to be struck between these two contrasting objectives, and that balance is struck with the help of this parameter lambda. This lambda parameter basically tells me how important it is to make the W sparse with respect to fitting the data. So now the question might arise, what is the function f which takes low value when W is sparse and high value when it is not sparse? The answer to that question is the L0 norm, which is simply the number of non-zero elements in W. Okay. So like we can use that as, so like you can understand that by definition that this will have the property which I mentioned. So we can use this L0 norm of W as the regularizer function, but the problem is that this is a non-differentiable function, as you can understand. So like we cannot apply any of the standard optimization algorithms on it. So what is done? So we relax it by another function which we call as the L1 norm of W. And L1 norm of W is that it's the sum of the absolute values of the elements of W. Okay, so that is the this is a relaxed version of the optimization problem which we solved. So now the L1 norm of W, this becomes the FW. Okay, so like if I am able, now the property, this L1 norm has a property such that if I am actually able to carry out this optimization, then the W which I will get will be almost sparse. What is meant by almost sparse? Now most of its elements will be close to zero. If it had been the L0 norm of W, then it would have, like, all the elements would have been exactly, or most of the elements would have been equal to zero. In this case, what is will be achieved is most of the elements will be close to zero. Okay, so now if we come to so the process of solving this optimization problem, this is called what the famous lasso regression, which I talked about in the last class also. So this is the objective, the least square part, which was there in linear regression also, and this is the regularizer, the L1 norm regularizer, which I mentioned. So basically now what I have to find W and B so as to minimize this function. So this particular problem is called the lasso regression. Okay, so lasso is like it's an acronym. So it's basically talks about the shrinkage operator. Like we have to so like I'm not going into the details of how this lasso regression works, but you can know that this is like we can use some numerical methods to solve this problem, such as gradient descent. So in case of linear regression, we had solved it analytically by actually taking their derivatives and equating to zero and so on. In this case, I am not doing it. I won't be able to differentiate this L1 norm of W with respect to W. So what I will do, I will use some numerical methods such as gradient descent or subgradient methods. I am not going into the details of that, but usually that will not be important also, because so all these things are implemented in the sklearn package of Python. That is, you can carry out it is already there is a you can use these lasso regression models which are already in, or libraries which are already present in sklearn, so that you can use them. So the message which you need to take away is that it is based on so this is the problem, or this is the problem which you are trying to solve in case of lasso regression, and it is solved with the help of numerical methods such as gradient, or similar to gradient descent. Now I earlier talked about this lambda parameter to you. So what is this lambda? Lambda is basically the relative importance of this part with respect to this part. This part is trying to do what? It's trying to reduce the or trying to fit your data onto the model. This part is trying to enforce the sparsity. So here, if you like do this kind of an experiment, the same on a particular data set, you carry out the lasso regression with different values of lambda, what you will see is as follows. So as lambda increases, that means you are giving less and less importance to the prediction part and more importance to the sparsity part. So you can see that as lambda increases, the mean square error will also start increasing. Why? Because you are no longer giving so much importance to minimizing that error. On the other hand, as lambda increases, you will see that the W which you get becomes closer and closer to a sparse vector. That means most of its coefficients you see start coming down. The mean average value, the mean value of the coefficients also keeps coming down, and their maximum value also keeps on coming down until they finally become zero at a very high value. That means you get that it becomes converges to the zero vector. That you of course you do not want. You want a sparse vector where, or nearly sparse vector where most of the elements will be small, okay, or as close to zero as possible. That is what you achieve when you increase the value of lambda. Okay. Now the problem with what I discussed so far is that it is mostly based on like continuous values. Now what that is I talked about these ratings like which are of course like all continuous value, which are which are basically real numbers, or the average rating, which is definitely the y which you are trying to predict, is actually it's actually a real number, like you say 4.5 out of 5 or 4.1 out or 3.6 out of 5. It's basically a real number. So but what happens if like it's really we are looking for discrete values? The question here is, suppose the question changes to what or how much rating will this particular user give to the camera out of 5. So the average rating can be a real number, but for a particular user, for a particular item, the rating will have is of course a discrete number. It will have to be either 1 or 2 or 3 or 4 or 5. Okay, so in this case I cannot do something like linear regression, because I will not be able to like give a like I cannot afford to predict a real number. In this case I will have to say either 1 or 2 or 3 or 4 or 5. Okay, and also suppose, and what if I did not actually have all those like intermediate features? That is, earlier I was saying that for each of the features, individual features, I have the score that is the xij, basically the feature specific score. Suppose I don't have that also. Okay, I simply have the list of features and I have the overall rating given by the user to the item. So then in such a situation, what do I do? Okay, so in that case also I will have to identify which features are important, but not in the framework of this linear regression. That is, it will no longer make any sense for me to have a W vector and use it to predict the total final feature Y. Why will it not make sense? Because W, that is neither will the final Y be a real number as happens if I go for the linear regression route, the WX route, and nor do I have the individual X's. For the individual features, I do not have the ratings now. So then I cannot do what I did in case of linear regression. So what I have to do in this case is, but still I need to find out which are the important features. Okay. And now now let us again come to this particular example. So let us talk about this video camera, in which we are focusing on one particular user, and we are trying to predict let us say that this is a particular video camera whose specifications are these. Okay, like it belongs to the company C2, its color is black, its resolution is 15 megapixel, its video rate is 30 frames per second, its price is $250, and the question is how much rating out of 5 will our customer give to this camera? Okay, that's the question. So to answer that, we go into her rating history. That is what ratings she has given to the older cameras. So here are some example ratings. This is a small data, a small snapshot of the data, but we'll come to the bigger data. But let us try to understand what it probably means. So here, if that is it may happen that this customer, she may consider some of the features to be more important than the other features. It may, for example, it may happen that for her the company and video rate, these are the important features for her, the other features are not important. It may happen, I'm not saying this that is what will happen, but it may happen. So then what happens here is that, so like here if you look at company, so here you may observe, forgetting this past feature C2, it may happen that she has a bias towards company C2 and a bias against company C1. That is, like if we look at her ratings earlier, it may appear that she gives poor ratings to company C1 and higher ratings to company C2. On the other hand, it also appears that if the video rate is low, then she tends to give low ratings, and if the video rate is high, then she may give high ratings. Okay, now this is not to suggest that whatever ratings she gives are driven by company or video rate or anything like that, but these seem to be like at least correlated to the choice which she is giving, even if these are not actually causal factors. There seems like it seems that such a relation does exist, that if the company is C2, then her ratings will be high, or if the video rate is high, then her ratings also will be high. But the same we may not be able to say about some of the other features, like say color or price. Okay, so like it may happen that she has given high ratings to some cheaper cameras and low ratings to some more expensive cameras. But on the other hand, the cameras to which she has given the highest rating is actually an expensive camera. So it's possible that the price feature does not really is not really so important to us. So if one way to understand this is going for a breakup like this. So suppose I am looking for this for that is the like for this particular feature called company. Another feature called color. Let us look at a breakup of her ratings. So overall, let us say that overall so far she has rated some 100 cameras, and to each of the features given here, these are the counts of the different ratings that she has given. That is, out of the 100 cameras, she has given a rating of 21 to rating of 1 to 21 cameras, which is the lowest. She has given a rating of 3 to 18 cameras, of 5 the highest one, to 17 cameras, and so on. So you can see that like it's pretty evenly distributed. She has giving ratings with equal frequencies. But if now suppose we split the data set on the basis of the company feature, say C1 and C2. So it turns out that the C1 feature, all the cameras in the C1 category, here she seems to be giving lower ratings, and in the C2 company cameras, she seems to be giving higher ratings. On the other hand, if we look at the color feature, so there are she has rated 70 black cameras so far and 30 white cameras so far. So in the 70 black cameras, so this is the the rating distribution, and here are the feature distributions in case of the white cameras. So now, based on these observations or based on these breakups, what can you say? Can you say something about her priorities about the different features? Yes.
So she prefers company C1 more than company C2. That is evident from the fact that she gives more rating to company C2. Sorry, she prefers company C2 more than company C1.
Right. And about color?
Sir, it has some relevance, but not as much as the company feature. You can
Right.
see that color white, the rating of color white increases slightly, and that of color black, that it decreases slightly.
Okay. Yeah. I guess yeah. So you're right. So like it's self-evident that she is giving like it seems that if the companies are like if the camera is from C1, most likely it will get poor ratings. Now it may like if the company is C2, it may get high ratings, but such a thing cannot be said confidently about the black or white, about the color feature. So it seems that C2, the company is a bigger determinant behind what ratings she gives. Now, it may not be that why this is the case, it may differ. Like for example, it may happen that she has some bias against this company C1 or some bias towards this company C2 because of which this is happening. But it may also happen that this company C1 provides some extra features or the cameras from company C1 have some particular characteristics which she does not like, but which is not recorded in this set of features. Similarly, the same in case of C2 also. And that is what she is rating is not really on the basis of these companies C1 and C2, but it's on the basis of those hidden or unknown features, but it is manifested through these companies. So that is also possible. Which one has happened, of course I am not going into it, but at least as far as this data set is concerned, we can say that the company is more important for her ratings than the color. Okay. So now based on this, we come to a concept known as a discriminative feature. Now what do I mean by discriminative feature? Discrimination, so it basically means separation. That is such a discriminative feature is such a feature which enables us to separate. Now separate between what? Now in this particular case, separate between low ratings and high ratings. So for the ease of the analysis, let us, so although 5 different ratings are possible, so for the ease of analysis, let us for the time being consider just group those 5 ratings together to get only two ratings, low and high. Okay, so 1, 2, 3, 1, 2 and 3 are low ratings, 4 and 5 are high ratings. So here, like if we go back to the data set and just take another, just group the ratings accordingly, you will see that out of the 54 C1 company cameras which she has rated, 43 have low ratings, 11 have high ratings. But if you consider company C2, then 20 have low ratings, 26 has high ratings. But if you consider overall, irrespective of company, you see 63 has low ratings, 37 has high ratings. Okay, so now, but on the other hand, if you consider, say, another feature called, say, whether the price is less than 300 or not. Again, the price is something which can take any value, but again, for the ease of representation, let us just binarize the price to two groups. Either the price is less than 300 or the price is more than 300. Okay, so in this case, again, we get a similar breakup. Here also, we get a similar breakup. Okay, so now, so similarly, like we can break up, like instead of 300, if I want, I can break up in other ways also if I want. So it's like how we will split the different features or which features we will binarize, that is up to you. So I'm just, what I'm showing right now is just to explain the concept. So now suppose what I am trying to estimate is what is the probability that a camera from company C1 is going to get a high rating. Okay, so that's the question which I am trying to answer. So this probability obviously can be estimated through relative frequencies like this. So it's like we are basically saying that she has rated 54 cameras from company C1. Out of those 54, 11 have got high ratings. So we can say that on an like 11 by 54 is the probability that a random camera from company C1 will get high ratings, and so on. So now if I again look at this table, what it is telling me is that if a camera belongs to company C1, then there is very low probability that it will get high rating. It's almost certain that it's going to get low ratings. But if the company is C2, sorry, this will be C2, there's a typo here. If the company is C2, then the probability that it will get high ratings is much higher. In fact, that is 0.55. Okay, so that means so basically uh, we can say that this company, this seems to be a discriminative feature in the sense that it is that is, if company is C1, then the probability that it will get high ratings is low. But if the company is C2, then the probability that it will get high ratings is high. So there is a clear difference between these two probabilities. But the same cannot be said about this price, whether price is less than 300 or not. If the price is for those cameras whose price is less than 300, the probability of getting high rating is 0.36. But among those cameras where the price is greater than 300, among them the probability of getting a high rating is 0.4, when there is hardly any difference between these two. So we can say that this whether the price is less than 300 or not, it does not seem to be a useful feature. That is, it's not able to differentiate much between these two quantities. Unlike this case where there is a clear daylight of difference between the two probabilities. If we, instead of say price less than 300, suppose I consider another, like instead I am trying to binarize this price, but instead of thresholding at 300, let us say I threshold it at 500. Okay, and suppose it turns out that there are 90, she has rated 90 cameras which are cheaper than $500, and 10 cameras she has rated which are $500 or more, whose cost is. Okay, and it turns out that in the first case, among the cheaper cameras, the probability of getting high rating is 0.4, and among the more expensive ones, the probability of getting a high rating is 0.2. So again, in this case, we can say that there is a difference between these two, but the problem is that there are only 10 cameras, expensive cameras, on the basis of which she has given these high ratings. So so although here there is a gap between these two probabilities, there are very few examples to to come to this which are so that is on only on the basis of only 10 examples I may not want to come to a decision. So that way, this feature, the company feature, seems to be more robust, and it's more discriminative. So these forms the basis of the decision tree algorithm. So what happens in case of decision tree algorithms? We are basically trying to identify which are the most discriminative features, and use once you have identified that, make you use that discriminative features to make your predictions. Okay. But the question is, how do I define discriminativeness? That is, intuition I have given, that is, here I am saying discriminative because here the difference between these two things is high, these two probabilities is high in this case, so it's discriminative. In this case, the difference in probabilities is low, so it is not discriminative. But how do I quantify that mathematically? So it's 6 p.m. but I will take about 10 minutes of your extra time today. So this kind of discriminativeness can be quantified by this quantity known as entropy. So entropy is a concept which you must have come across earlier in thermodynamics or chemistry and some and other topics. So so basically, so here also we will define something known as entropy of probability distributions. And let us try to ask this question about how this kind of a discriminativeness can be quantified. Okay, so let us look at the definition of entropy. So now consider probability. So before coming to the formal definition of entropy, let us consider two probability distributions. Okay, two coins, let us say. Okay, a biased coin like this, which has, let us consider y equal to 1 means head and y equal to 2 means tail. Okay, so it's since it's a coin, there are only two possibilities, head or tail. So in this case, probability y equal to 1 is 0.9, means there is 90% probability that you will get head, and there is 0.1 probability that you will get a tail. Now in this case, in the here it's a unbiased coins, which means that both head and tail are equally likely. Okay, so now suppose I have given you these two coins. One is an unbiased one and the other is a highly biased one. Now you can say that, so then if I ask you which of these coins has more information, so in that case I will have to say the answer has to be that the second coin has more information, in the sense that even before the toss is conducted, I can already say with a lot of confidence that you are going to get a head. In this case, however, unless you actually toss the coin, you will not. There is no way to say whether it's going to give a head or tail, right? In fact, if you toss it 10 times, you will probably get 5 heads or 5 tails. In this case, if you toss it 10 times, you'll probably get 9 heads, right? So basically, clearly, this has high amount of information, or in other words, this has high discriminative abilities. Like if you are considering a, and that is in, like if you considering a particular feature which takes two values. For one value, the probability of getting high ratings is 0.9. For the other value, the probability of it getting high ratings is 0.1 or something like that. So clear in that's clearly it's a that feature is discriminating between the on the overall outcome. Okay, so on the basis of this, I define this quantity known as the entropy. This is how it is defined. Okay, so there is a probability distribution, a probability. So if like so in case it's a binary variable, like there are two probabilities: the probability of y equal to 1 and the probability of y equal to 2. But here, of course, we are talking about like if in so here like if we are talking about a say 5-class classification, if we are trying to predict whether the label is going to be 1 or 2 or 3 or 4 or 5, then of course there will be 5 different probability values. Each of it's a probability mass function defined on with a support set of 5. So each of those, so there will be P1, P2, P3, P4 and P5. So based on that, you can calculate this quantity, which I am defining as entropy. Now, for a distribution like this, if the case is equal to like if it's for case 1, in that case the the entropy is this thing, and here that is you can actually calculate it. That is, in one case the entropy will be high, in the other case the entropy will be low. Now this entropy will be the lowest in that kind of an extreme distribution where one of the probabilities is 1 and all the other probabilities are 0. Because that is to say, let us say there is a distribution for which P1 is equal to 1, P2 is equal to 0. So in that case, what happens to the entropy? So it becomes P1 times log P1 minus P1 times log P1 minus P2 times log P2. Now P1 is 1, that means log P1 is 0. So the first term will be 0, but P2 is also equal to 0. So the second term will also be 0. So that means your H will become equal to 0. The entropy will be 0. So that means what, for distributions with high discriminative abilities, the entropy is 0. For in case of low discriminative or I mean low, closer to 0, if the discriminative ability is low, then the entropy is closer to 1. Okay. So now, so this entropy basically forms a basis on which you can select the features. So before you have selected any feature at all, so that is in that case your data set will have certain entropy. So let us see this example. We will stop after understanding this example. So let us say that like suppose there is no split. This is the total data set. There are 100 cameras, out of which our user has given low ratings to 63 and high ratings to 37. Okay, so basically the probability distribution which we are considering here is 63 by 100 and 37 by 100. Our P1 is 63 by 100, our P2 is 37 by 100. Okay, so based on that, I calculate this entropy now. Therefore, for such a distribution where P1 equal to 63 by 100 and P2 is equal to 37 by 100, you can just check that the entropy will come out to be 0.66, okay, which is some reasonably high value. Now, if you consider the examples for which company is C1, okay, and here, so here you can see that there are total 54 examples, 43 out of which are in this group and 11 are in this group, okay. So in this case, what is your P1 going to be? your P1 is going to be 43 by 54. And what is your P2 going to be? P2 is going to be 11 by 54. Right? And then if you actually do the calculations, you will see that this entropy has come out to be 0.51. What do I mean by split entropy? So basically you have used the company attribute to split the dataset. The dataset had 100 cameras. Now 54 of them are in company C1, 46 have company C2. That means basically you are those 100 cameras you are splitting into two groups of size 54 and 46 respectively. Now in the first split, those which are for company C1, the entropy is this thing 0.51. If you consider the second split C2, the entropy is 0.68. Okay, so now like the two splits also have a size. They are not equal splits. One is of size 54 by 100, the second is of size 46 by 100. So then based on this, you can calculate what is known as the information gain according to the formula which has been given to you. So this formula basically what it shows you is that so if you did not split, then you would have got an entropy of 0.66. But if you do split, then you are like in one of the subsets you get an entropy of 0.51, which is lower. In the other one, I get an entropy of 0.68, which is slightly higher, but pretty much the same. So that means what overall I can say that I have that splitting on the basis of this feature gives me a set which has lower entropy, a subset which has lower entropy. Now, as I was telling here also, low entropy means what? Low entropy means like a more polarized distribution, which is biased towards one side. And if you have this kind of a distribution which has low entropy, then it's easier for you to take a decision on, or it's easier for you to make a prediction. So this distribution, for example, it had low entropy, and in this case it was easier for you to make the prediction, right? In this case the prediction being that y is will be equal to 1. So similarly in this case also, because it's a biased distribution, so it has low entropy, so like it in this case you will be able to make a decision more easily, a prediction more easily, and of course the prediction is going to be low ratings. So if you know that the company is of C1, then without thinking much, you can say with reasonable confidence that our customer is probably going to give a low rating to that camera. Okay, so you will be able to say it more confidently than what you could have said if you did not know the company. Okay, so this basically forms the basis of feature selection on the basis of entropy. So now suppose there are multiple features like this. For each of the features can split the data set in this way. And so you, like after splitting, you can get the entropy also. So from each feature, you can calculate the information gain. What is information gain? The information gain is basically the entropy before splitting minus the total entropy after splitting. Initially, there was one dataset of 100 elements which had this entropy 0.66. After splitting, there are two subsets of size 54 and 46 whose entropies are these two things. So like it's the information gain here is basically original entropy minus final entropy. Of course, we have to balance for the sizes. So here we can see that if for the different features, we will be able to get different values of information gain. So now let me ask you this one question. So is it good to, do I want a feature whose information gain is higher or information gain is lower? You answer this question and we will stop the class. Do I want to increase the information gain or decrease the information gain?
I want to increase the information gain.
And why so?
Sir, because in deciding the entropy, if I split it and the entropy of the leaf nodes comes to be more, then that is a good thing for me, because I am more confident in my decisions and I have more confidence in predicting.
Right. Right, right. So basically, like if I am able to reduce the entropy, then I am able to make predictions more confidently. And if so, basically after splitting, the entropy has to be less. And if the after splitting the entropy becomes less, that means my information gain is more. Okay, so I want the information gain to be higher. So each of the different features is giving me some information gain. So what I will do is I will select that feature which gives me most information gain. Okay, so the what we get like that is called the information is called the decision stump. So that is, you have a data set like this, you split it on the basis of that feature which gives you the highest information gain. In this case, that's the company feature. So accordingly, we decide to we come up with a simple prediction rule like this. I look at the company feature. If it is C1, then my prediction is going to be low ratings. If it is C2, then my prediction is going to be high ratings. As simple as that. Now this thing I can extend to more features, which we will discuss on Thursday. Okay, I know that we are past time, so let me stop here. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, everyone.